Welcome to Logical Verification 2020-2021. This video is about Chapter 12, Section 6, Order Type Classes in Lean. When you think of an order, you probably think of something like the natural numbers with the less than or equal relations. You have 0 is less than or equal 1, 1 is less than or equal 2, and so forth, 3, and so forth. So this is one good example of an order to keep in mind. However, there are lots of other relations that look very similar. Another good example to keep in mind is the order on sets. So this is like the natural numbers with the less than relation. Another one is the, for example, the sets of natural numbers with the subset relation. This also forms an interesting order. A good idea, a good way to visualize this is by drawing a diagram like this. Is to think of this as having the empty set, which is a subset of the singleton 1. It's also a subset of the singleton 2. It's also a subset of the singleton 3, and so forth. And now, of course, the singleton 1 is a subset of the set containing 1 and 2. 1 and 2, and the set 2 and 3 has the singleton 2 as a subset sets and the singleton 3 as subsets, and so forth. So the reason why I'm drawing these two examples is because this order here, it's a line, it's very linear, while this one is not linear. There's maybe a good example to keep in mind. We also want the subset relations to be orders. And just as with the structures that have one binary operations, also here for the orders, we have certain sets of axioms and a corresponding hierarchy of structures. So we start with a pre-order, which is kind of the bare minimum you can ask from an order relation. There's a lot of stuff that already works on pre-orders. Pre-order is just a relation that is reflexive. So when we're always thinking of relations like less or equal than, and of course less or equal than should be true for if you have for equal elements. So this is called reflexivity. And the other property that we require of a pre-order is transitivity. So if 0 is less or equal 1 and 1 is less or equal than 2, then 0 is also less or equal than 2. And similar here, if the empty set is a subset of the singleton 1 and the singleton 1 is a subset of the set 1, 2, then also the empty set should be a subset of the set containing the elements 1 and 2. Transitivity. And just as we extended a semigroup to a monoid by adding more and more axioms, we can also extend orders. So the next extension is a partial order, so-called partial order, which is now, in addition to those two axioms, also antisymmetric, which means that if two elements are, so if x is less or equal than y and y is less or equal than x, then they must be equal. Okay, so in both of those examples, this is actually true. However, there are other orders, even ones that we have in Lean, for example, the lists with the subset relation. There we have that. So the subset relation of lists in Lean is defined as the subset of the. So two lists are subsets if and only if their corresponding sets are subsets. So 1, 2, 2 is here a subset of 1, 2. And vice versa. So also 1, 2, the list 1, 2 is a subset of the list 1, 2, 2. So just comparing the elements, not how often or in which order they occur. And hence, the lists with the subset relation lean, they are not antisymmetric. But they're still a preorder, and we can use all the lemmas that we prove for preorders also for lists with the subset relation. Yes, right. And then the difference between this order here of the set of natural numbers with the subset relation and the natural numbers with the lesser equal relation, the one thing that strikes out is that this one here is very linear. So we do not have this kind of branching where we have elements that are not comparable to each other. Instead, every element can be compared with every other one. Like when either 0 is lesser or equal than 1 or 1 is lesser or equal than 0. And this is what we call a linear order, or sometimes also called total order. And for this, any two elements can be compared either one way or the other. Okay, and in Lean, these types are called exactly like this. They are type classes. And yes, we can define these type classes also in our own types, just as we do with any other type classes. So here we have an example of defining a preorder on lists. So not the one that I showed you on the whiteboard, but instead preorder where two lists are compared on the length, not on the elements that they contain, but on the length instead. And this is another preorder. And preorder that is not antisymmetric, because you can have two lists of the same length that are not equal, obviously. At least if alpha contains more than two elements. And right. Exactly. So this is in general not a preorder. Just not a partial order, it's just a preorder. Now we've already seen another kind of order structure in chapter 10. This is where complete lattices. So the lattice always gives you an order relation. So by setting that x is less or equal than y, if the meet of x and y is so you can always go from a lattice structure to an order structure, and hence we have a different type classes for lattices, which contains the operation, the meet and join operations, and then there's an instance which derives a partial order from this lattice structure by defining the relation in the appropriate way. And another common thing is that the order relation can be compatible with operations of the type. We had semigroups, we had monoids, and it's often the case, I think it's the natural numbers, that the operation of a monoid is, for example, monotonic. So if you have two natural numbers m and n, and you look at m plus n, then this only gets larger if you make m or n larger. This is not just true for natural numbers, it's also true for lots of other numeric types. Hence we have type classes that have additional axioms relating the order and the operation of the type. And these are like the main ones that we have here. So we have ordered monoids, we have ordered semirings, commutative rings, fields. You can look at the definitions to look at the axioms that they have. The main idea here is that these generalize various numeric types like natural numbers, rational numbers, and so on, and allow us to prove the same theorems for all of those types once and for all.